So in this lecture, I will discuss convergence of random variables. So there will be a probability space which is fixed once for all. And on this probability space, we will have a sequence of random variables defined on it, and sometimes a limit, which is also a random variable defined on the same space. And I will first define what I understand by almost sure convergence. So it would be natural to say that xn converge to x if for all omega in omega, xn omega converge to x of omega. But, well, this is too demanding, so we will weak this convergence to this almost sure convergence. So I'll say that a sequence xn of random variables converge to a random variable x almost surely or almost everywhere if and only if there exists a set A in the sigma algebra F such that the probability of A is equal to 1. So this is well defined because A belongs to the sigma algebra. And for all omega in A, xn of omega converge to x of omega. So we are not requiring anymore that xn of omega converge to x of omega for all omega, but just for those on a probability on a set A whose probability is equal to 1. So let's assume that we have a sequence xn converging to x almost everywhere. I want to transform this in a statement of probabilities. So what does it mean that xn of omega converge to x of omega? Well, this happens, as you know, that if and only if for any epsilon positive, we can find an integer n such that for all m larger than n, then xm of omega minus x of omega, it's bounded by epsilon. Let's say less or equal than epsilon. So I want this statement to become a countable statement, so let me replace this condition for all epsilon with the condition for all k larger than 1, and let me put here 1 over k. So this means that if xn of omega converge to x of omega, this means that omega belongs to the following set. Well, we want that for all k, which means for all k larger than 1, there exists an n, so there exists an n larger than 1, such that for all m larger than m, this happens. So omega belongs to the set of omega prime in omega such that x m of omega prime minus x of omega, it's less or equal than 1 over k. Mind that this set here, which I will write for short as xm minus x is less or equal than 1 over k, that this set belongs to the sigma algebra because I'm assuming that xm and x are random variables. So for each m and k, this set belongs to the sigma algebra, and therefore the intersection, well, intersection in k, the union in n, and intersection in m larger than n also belongs to the sigma algebra F. And what I know is that, well, xn of omega converge to x of omega if and only if omega belongs to this set. This means that xn converge to x almost everywhere. Well, if and only if this set has probability 1. So this happens if and only if the probability of that set, which means the intersection of all k larger than 1, the union n larger than 1, the intersection m larger than n, of xm minus x smaller than 1 over k, that this set has probability 1. So now I have a statement concerning the almost sure convergence. If I want to prove that xn converges to x almost everywhere, I have to prove that the probability of this set is equal to 1. Well, let's consider this set, and let's try to simplify this expression. So what I claim is that, well, first of all, if the intersection of sets has probability equal to 1, this means that this is equivalent to say that for all k, the probability of this set is equal to 1. So this happens if and only if, for all k larger than 1, the probability of the union of n larger than 1, the intersection of m larger than n, of xn minus xm minus x smaller than 1 over k, it's equal to 1. Therefore, if I want to prove that xn converges to x almost everywhere, actually I have to prove that this probability is equal to 1 for all integer k. And this is the same thing as requiring that for all epsilon positive, this probability that it's less than epsilon, it's equal to 1. So we have a simpler statement. If we want to prove that xn converges to x almost everywhere, we have to show that for all epsilon positive, the probability of this set is equal to 1. Now, let me simplify that further by calling this set Bn. So Bn is the intersection, and epsilon is fixed. So Bn is the intersection for m larger than n of the event, the set that xm minus x is less or equal than epsilon. Mind that as n increase, I'm doing an intersection on smaller and smaller sets. This means that as n increase, this set increase. So this sequence, Bn, it's a sequence of increasing sets. And when this is the case, Bn is converging to the union of Bn. And the probability of Bn is converging to the probability of the union of Bj. So this means that this probability here is actually equal to the limit as n converges to infinity of the probability that the intersection of m larger than n, that xn minus x smaller than epsilon, that this is equal to 1. So let me repeat this argument to make sure that it's understood. Let me call Bn this intersection. What I'm saying is that if when n increase, you're doing intersection on smaller number of sets, which means that Bn increases. So Bn, it's a sequence of sets which is increasing in the sense that if n1 is less or equal than n2, then Bn1 it's contained in Bn2. And, well, these sets, since they are increasing, they are converging to their union. And we have seen in measure theory that when you have a sequence of sets increasing to a set, the probability of this set is converging to the probability of the union. So this means that since these sets are the sets Bn, that the probability of Bn is converging to the probability of the union, which means that this probability is equal to this limit. And now we reached a statement about almost sure convergence. So let me write what we proved. We proved the following result. So maybe let me call that a proposition. We just prove the following proposition. A sequence xn of random variables converge to a random variable almost everywhere if and only if for all epsilon positive the limit as n goes to infinity of the probability of the intersection for m larger than n of the set xm minus x smaller than epsilon, it's equal to 1. Of course, I can take, well, this limit it's equal to 1 if and only if the probability of the complement is equal to 0. So this happens if and only if the limit as n goes to infinity of the probability. So what's the complement of this set? Well, it's the union of m of this event being larger than epsilon. So this is the union for m larger than n of xm minus x being larger than epsilon equal to 0. Therefore, if you want to prove that the sequence xn converges to x, you have to show that for any epsilon positive, this limit is equal to 0. So now we have a more or less simple formula to prove whenever we want to prove that some sequence converge almost surely to a random variable. Now, let me introduce a second type of convergence which already appeared in the previous lecture. So I will say that xn converge to x in probability, and this will be represented by this symbol, if and only if for any epsilon positive, the probability that xn minus x is larger than epsilon, that this converges to 0. So I'll say that the sequence converges in probability to x if for any epsilon, this probability is converging to 0. And a simple lemma, which I want to prove immediately, tells you that, well, if the sequence xn converges to x almost everywhere, then xn converges to x in probability. And this is very simple. You have just to remember the formula we proved. Assume that xn converges to x almost everywhere. This means that for any epsilon positive, the limit in n of the probability of the union for m larger than n, that xm minus x it's larger than epsilon, that this is equal to 0. We have seen that this is a necessary and sufficient condition for the almost sure convergence of the sequence xn. Well, but this union certainly contains the set that xn minus x it's larger than epsilon. And since this union contains the probability of this event, it's bounded by that one. Since this one converges to 0, and this one, the probability of this event is positive, this implies that the limit, as n tends to infinity, of the probability that xn minus x it's larger than epsilon, it's equal to 0. since this holds for any epsilon, we just proved that the sequence xn converges to x in probability. Therefore, we just proved that if xn converges to x almost everywhere, it converges in probability as well. We just proved that if a sequence converges almost surely, it converges in probability. Let me now state a type of converse result. So I'm assuming now that the sequence xn converges to x in probability, and what I claim is that we can construct a subsequence nk such that x and k converge to x almost everywhere. So that any converging sequence in probability has a subsequence which converges almost surely. So let's prove this result. We know that xn converges to x in probability. This means that for all epsilon positive, the limit as n goes to infinity of the probability that xn minus x is larger than epsilon, that this is equal to 0. So now let's fix k, an integer k larger than 1, and let me take epsilon equal to 1 over 2k. So, since this is true for any epsilon, I know that the limit as n goes to infinity of the probability that xn minus x larger than 1 over 2k, that this is equal to 0. Since this probability is equal to 0, as n goes to infinity, this means that there exists nk such that the limit, such that this probability that xn minus x is larger than 1 divided by 2 to the power k, that this is bounded by 1 over 2 to the power k for all n larger than nk. So we can find this sequence nk. I want this sequence to be an increasing sequence, so we will proceed by induction just to make sure that this sequence nk is increasing. So let's assume that, well, you first choose n1, then let's assume that you chose n1 up to nk, and now you find nk plus 1. Well, if nk plus 1 is larger than n1 nk, you don't change it. But if nk plus 1 is smaller, which means that it's less or equal than nk, you change the definition of nk plus 1, defining it as nk plus 1, just to make sure that this sequence is increasing. Of course, if this is true for all n larger than nk plus 1, and nk plus 1 is smaller or equal than nk, this is also true for all n larger than nk plus 1. Therefore, by changing the definition of this sequence, you can make sure that this sequence is an increasing sequence. And now what I claim is that the sequence x and k converge almost everywhere to x. So this is my claim, and what I will need for that is this inequality. Notice that this inequality holds for all n larger than nk. In particular, it holds for nk. So what I will be using is this estimate in order to show that x and k converge almost everywhere to x. So I will erase everything, just keep this bound and prove this statement. So in the previous stake, I constructed a subsequence nk with this property. So which means that the probability of this event, it's bounded by 1 over 2k for all k larger than 1. And from this estimate, I want to conclude that x and k converge to x almost everywhere. So we have seen that in order to prove that a sequence converges almost everywhere to x, we have to show that for all epsilon positive, the limit as k tends to infinity of the probability that the union for L larger than k of the set x and L minus x larger than epsilon, that this quantity is equal to 0. So let's prove this statement. In order to prove this statement, well, you have to prove it for all epsilon, so fix an epsilon. And now you have to show that this limit goes to 0. So for that one, I will prove that I will fix a delta, and I want to prove that there exists a k0 such that for all k larger than k0, this probability it's less than delta. Right? In order to prove you fix an epsilon, in order to prove that this limit goes to 0, means that, well, for all delta, you can find k0 such that if k is larger than k0, then this inequality holds. So now epsilon and delta are fixed, and we have to find k0. So let's consider k0 such that 1 over 2k, it's k0, it's bounded by epsilon, and 1 over 2 k0, it's bounded by delta. So let's fix k0 with these two properties. Let's consider k larger than k0, and let's prove that indeed this probability is bounded by delta. Well, first, since 1 over 2 k0 it's less than epsilon, and k it's larger than k0, this means that 1 over 2k it's less than epsilon, and this means that if this probability, if this event is larger than epsilon, then it is larger also than 1 over 2L. What I'm saying now is that I'm assuming that k is larger than k0, and I'm saying that under this condition, this event is contained in that one. To prove that this event is contained in this one, I have to show that epsilon is larger than 1 over 2L. But this is true because since L is larger than k, 2L, 1 over 2L, it's smaller than 1 over 2k, which is smaller than 1 over 2k0, which is smaller than epsilon. So indeed, this event is contained in this one for L larger than k, and therefore this union, it's contained in this union, which means that this probability is bounded by this probability. Right? So it follows from the property of k0 that this union is contained in that one, and therefore that this probability is bounded by that one. Now, let me bound the probability of the union by the sum of the probabilities. So I don't have much space, but let me write that this is bounded by L larger than k, that the probability of x and L minus x is larger than 1 to the power 2L. So this I'm using here, that the probability of the union is bounded by the sum of the probabilities. Now let's use this property here with k equal to L to bound this probability by 1 to the power 2L. So this expression here, it's bounded by the sum for L larger than k of 1 over 2L, and this is equal to 1 to 2k minus 1. So if I choose here such k0, not with k0, but k0 minus 1, 1 over 2k, it's bounded by minus 1, it's bounded by 1 of 2k0 minus 1, which is bounded by delta. So this proves that this is indeed bounded by delta. And therefore, we proved that indeed this limit converges to 0, which means that the sequence x and k converge to x almost everywhere, as I claimed. Let me introduce a new concept of convergence, which is convergence in LP. So P will be a real number between 0 and plus infinity, and I will say that the sequence xn converges to x in LP if and only if the expectation of xn minus x to the power p converges to 0 as n goes to infinity. So I already proved that convergence in LP implies convergence in probability, but let me state it again and prove it again to make this lecture self-contained. So what I claim is that, well, if xn converges to x in LP for some p between 0 and plus infinity, then xn converges to x in probability. And the proof is elementary and relies on Chebyshev inequality. So in order to prove that xn converges to x in probability, I have to show that for all epsilon positive, the probability that xn minus x is larger than epsilon converges to 0 as n goes to infinity. But now this is this probability, so let's fix epsilon. Let's prove that this probability converges to 0. So let's consider the p, which appears in the hypothesis of the lemma. And this probability is equal to the probability that xn minus x to the power p, it's larger than epsilon to the power p. Apply Chebyshev inequality to bound this expression by 1 divided by epsilon to the power p, the expectation of xn minus x to the power p. And by assumption, since xn is converging to x in LP, this expression converges to 0 as n goes to infinity, which proves that this one converges to 0 as n converges to infinity, and this is the statement of the lemma. So let's prove a type of converse. So this is a theorem. I'm assuming that the sequence xn converges to x in probability, and I'm also assuming that this sequence is bounded by a random variable y, and that the expectation of y, so see that y is non-negative, that y to the power p is finite for some p between 0 and plus infinity. So these are the assumptions. I'm assuming that xn is converging to x in probability, and that the sequence is bounded by a random variable y, which is non-negative, and such that the expectation of y to the power p is finite for some p between 0 and plus infinity. And what I claim is that this entails that the sequence xn converges to x in LP, the same p which appears here. And the proof is also quite simple. We have seen that since xn converge to x in probability, that there exists a subsequence which converge almost surely to x. Well, therefore, almost surely x, which is the limit of xn k, xn k is bounded by y, so this means that x, the absolute value of x, it's bounded by y almost everywhere. Right? There is a set here with probability 1, such that for any omega in this set, xn k of omega converge to x of omega, which means that for all omega in this set, x of omega is bounded by y, which means that x, the absolute value of x, it's bounded by y almost everywhere. And since x is bounded by y almost everywhere, and when you take expectation, null sets have no influence, we deduce from this inequality that x, the absolute value of x to the power p, it's bounded by the expectation of y to the power p, and this is finite. So that this is less than the expectation of y to the power p as well, because we have this inequality. Now we are ready to prove that xn converge to x in LP, so we have to bound the expectation of xn minus x to the power p. We will decompose this expectation in two pieces. The first one, so we fix an epsilon positive, and we decompose this expectation according to xn minus x p, it's larger than epsilon, or it's smaller than epsilon. So this is the piece in which xn minus x is larger than x and epsilon, and then there is a second piece in which I'm assuming that xn minus x is smaller than epsilon. So remember that chi represents the indicator function, so here I'm taking this expectation on the points at which xn minus x is larger than epsilon, and here on the points in which xn minus x is smaller than epsilon. Now, if xn minus x is smaller than epsilon, this means that xn minus x to the power p is bounded by epsilon to the power p. So this expression, this second expectation, it's bounded by epsilon to the power p, right? Xn minus x is less than epsilon, so this expression is less than epsilon p, and here chi, the indicator function, is bounded by 1. The expectation of this function bounded by 1, it's bounded by 1. Now we have to consider the second term. Well, for the second term, now I will use the fact that xn, it's bounded by y, and that x, it's bounded by y. So since xn, so maybe let me write it here, I have xn minus x. This is bounded, of course, by xn plus x. Both terms, xn is bounded by y by assumption, and we proved that x is bounded by y almost everywhere. So this is bounded by 2 times y almost everywhere. And therefore, I can estimate this first expectation by 2 times power p, y, which is positive, to the power p, times the indicator that xn minus x larger than epsilon. Now I claim that this expectation converges to 0. Indeed, we have here a random variable, y, such that its expectation, it's finite. And then we have a family of sets. So let me call an the set in which xn minus x is larger than epsilon. And what we know is that the probability of an, it's converging to 0, because xn is converging to x in probability. It follows from this condition and this condition that the expectation of yp, the indicator of the set an, that this expectation converges to 0 as n goes to infinity. This is a result which has been seen in measure theory, and I will give you a reference in the notes of this result. So, from this condition, it follows that the limit as n goes to infinity of this first expectation goes to 0 because we bounded it by this one, and this one is converging to 0. So from this, we conclude that the limit, so we decompose this expectation in two pieces, one which is bounded by epsilon to the power p, and the other one which goes to 0 as n goes to infinity. This means, therefore, that the limit as n goes to infinity of the expectation of xn minus x to the power p, that this is bounded by epsilon to the power p. And since epsilon is arbitrary, we can send epsilon to 0 to conclude that indeed xn converges to x in LP as I claimed. So we have seen that we introduced in this lecture three concepts of convergence almost everywhere: probability and LP. We have seen that almost everywhere implies probability, and that probability implies subsequence, almost sure convergence of a sequence. We have seen that LP implies convergence in probability, and we obtained the reverse under the extra assumption that the expectations of that the xn, the random variables xn, are bounded by y, and y it's an element of LP. So this is what we proved. Now, well, I want to give you an example in which we have convergence in probability and we don't have convergence in LP. So I want to conclude this lecture with examples. So the first one is to show that convergence in probability does not imply convergence in LP. And the example, it's very simple. So let's take a p between 0 and plus infinity, and I'll find a sequence which converges in probability and which does not converge in LP. So more precisely, this sequence will converge to 0 in probability, but xn will not converge to 0 in LP. And the example is as follows. Well, you take as omega the interval 0, 1. The Borel subsets will play the role of the sigma algebra, and the Lebesgue measure, lambda is the Lebesgue measure, and p will be the Lebesgue measure restricted to the Borel sets. Now, here is my sequence. We are in the interval 0, 1. You fix n larger than 1. So here is 1 over n. And the function x and p looks like that. Well, it is equal to n to the power 1 over p in the interval 0, 1, n, and it's 0 everywhere else. So now I claim that this sequence, I hope this sequence is clear. xn, here's the graph of xn. xn, it's equal to n to the power 1 over p in the interval 0, 1 over n, and equal to 0 from 1 over n up to 1. So now I claim that xn converges to 0 in probability. So what we have to show is that for all epsilon, the probability that xn is larger than epsilon, that this goes to 0. So fix epsilon, fix an epsilon positive. What is the probability that xn is larger than epsilon? So you fixed an epsilon here. Let's say that n is larger than 1, and you choose epsilon smaller than 1. So if you want xn to be larger than epsilon, well, this happens in this interval. So the probability that xn is larger than epsilon, it's the probability of the interval 0, 1 over n. And since we are working with the Lebesgue measure, this probability is exactly equal to 1 over n. And 1 over n converges to 0. So again, you fix an epsilon. You ask yourself, well, what is the probability that xn is larger than epsilon? Since we are taking epsilon between 0 and 1, for xn to be larger than epsilon, well, this means that we are choosing a point here in this interval, and the measure of this interval is 1 over n. So it's indeed true that xn is converging to 0 in probability. Now let's compute xn, which is positive, to the power p, and let's compute its expectation. Well, xn to the power p in this interval 0, 1, n, it's equal to n. And xn to the power p in the interval 1 over n up to 1, it's 0. So this expectation, it's easy to compute, and it's exactly equal to 1. Which means that it's not true that the expectation of xn minus 0 to the power p converge to 0. This is not true because, well, xn minus 0, it's xn is positive, so this is expectation of xn, and this is 1, which does not converge to 0. So here is an example of a sequence of random variables xn, which converge in probability to 0, but which does not converge in LP to 0. And well, you can check that, of course, this condition does not hold. We cannot find a sequence y, which is in LP, such that xn is bounded by y for all n. We have just seen an example which shows that convergence in probability does not imply convergence in LP. So now let me give you a second example, which shows that convergence in LP does not imply almost sure convergence. Again, my example will be in the interval 0, 1. So this is omega. The sigma algebra will be the Borel 1, and the measure will be the Lebesgue measure, as in the previous example. And now let's fix a p between 0 and infinity. So I'll find a sequence xn which converge to 0 in LP, but xn does not converge to 0 almost surely. Mind that since xn converges to 0 in LP, it converges in probability, and since it converges in probability, we'll find a subsequence which converges almost surely. So there is a subsequence of xn which converges to 0 almost surely. But what we will show here in this example is that xn may not converge almost surely to 0. The example is very simple. I'll draw the graph. In step 1, well, we'll just define, so this is x1. x1, the variable is just identically equal to 1. Now in step 2, you divide your interval in 2 intervals. The first one, it's always closed on the left-hand side and open on the right-hand. So now you have 2 intervals, the interval 0, 1/2, and the interval 1/2, 1. So x2, so now we will define x2 and x3. x2 will be equal to 1 in the interval 0, 1/2, and 0 in the interval 1/2, 1. So x2 will be the indicator function of the interval 0, 1/2, and x3 will be the indicator function of the interval 1/2, 1. So now you can guess what the sequence is, but let me construct it on a further step. So here again we have the interval 0, 1. So this is 1, right? Now I will divide it in 4 intervals. And I define now x4, x5, x6, and x7. So x4 will be the indicator function of the interval 0, 1/4. So it's equal to 1 in this interval and 0 everywhere else. x5 will be the indicator function of the interval 1/4, 1/2, and so x6 and x7, and we follow in this way. So first I claim that xn converge to 0 in LP. Indeed, if you take x1, well, x1 is either 1 and 0, so x1 to the power p, it's equal to x, and therefore the integral of the function of x1, the expectation of x1, it's 1. Now the expectation of these functions will be 1/2. So in step 2, the expectation is 1/2. In step 3, the expectation it's 1/4, and so on. So you see that indeed xn is converging to 0 in LP. Now I claim that xn does not converge almost surely. Well, you fix any point. In the first step, well, it's equal to 1. In the second step, whatever the point you chose in the interval 0, 1, one of the two functions will be 1 and the other 0. So here, xn of omega, so you choose omega in this interval, and you look at the sequence xn omega. Here it's equal to 1. Here, either x2 is equal to 1 and x3 is 0, or the opposite. Here you see that one of them will be 1 and the others will be 0. So you'll have 1 among these 4 variables. 3 of them will be 0 and 1 of them will be 1. In step 4, you'll have 7 variables will give you 0, but 1 of them will give you 1. So you see that you can find a subsequence. So for all omega in 0, 1, you can find a subsequence nk such that x nk of omega it's equal to 1 for all k, and another subsequence mk such that x mk of omega it's equal to 0 for all k. And this shows that xn of omega does not converge. So for all omega, xn of omega does not converge because it has subsequence 1 which converges to 1 and the other one which converges to 0. So we have here an example of a sequence of random variables which converge to 0 in LP, but which doesn't converge almost surely to 0. And with that, I complete this lecture.